and I forgot to record all the cool words I said before, but it doesn't matter because we are going to introduce our first speaker. The title you're over there, but Ugo is a researcher at the Department of Astrophysics at CEA, actually, like a very long trip from here. I know that. Who is from France? Il parle français. Who doesn't speak French here? Okay. Who doesn't speak English here? Est-ce que la personne parle pas anglais? Il n'y a pas de problème? Well, we can always, translate and between French and English, no problem. So, yes, Ugo is from France, so he can also spoke a better French than mine. And this is postdoc at the CEA. Yeah. Okay. Before that, he completed his PhD in astrophysics at the ENS in Lyon. You read about this, right? But whatever, I'm repeating it. He specialized in star formation, and it's particularly focused on the study of dust dynamics, the formation of protoplanetary disk, so when stars are born. Okay? So you know what he's going to talk about. So I will not repeat what is written there. So help me welcoming Ugo to his talk.
Okay, I'm smaller than that. Okay, well, thanks very much for introducing me. I'm very happy to be here today to present what I'm studying. So I will be talking about how stars are born and what is hidden under the dust veil. And more honestly, I will be talking of how protostars are born. You will see what I'm talking about in a while. All right, first, I would like just to give you some idea of what is a stars. So stars are celestial bodies that are in hydrostatic equilibrium, which means that their gravity is compensated by their pressure. And so they can live for a very long time like that. I can give you some numbers for the sun, but the sun is not the only stars. It's a fairly typical one. So in terms of mass, you have to know that the sun is 10 to the power 30 kilograms. So that means that it's 2 and followed by 30 kilograms. So it's an enormous mass that is really unfathomable. And to compare to the Earth, make it a bit easier to understand. So the sun is basically 300,000 times the mass of the Earth. It's about 700,000 kilometers in radius, so almost 1 million kilometers. It's mostly composed of hydrogen. It's like 74%. There is also a bunch of helium. And on top of that, 1% of heavier elements that we typically call metal in astrophysics because we are very precise people. The sun is hot. It's hot at the surface. It's like 5,000, 6,000 Kelvin, but it's even hotter at the center. So at the center, the sun is 15 million Kelvin. So that's enormous. And this is so hot and so dense that matter can fuse together, hydrogen can fuse and make helium, which is why the sun is supplied with energy. So in terms of age, the sun is about 4.6 billion years old. So where do we find stars? So we find stars in galaxy. So of course, I cannot show you a nice picture of our galaxy where we see all the galaxy because we are sitting in it. So the second best candidate to take a nice picture is the Andromeda galaxy, which is seen here. It's a bit larger than the Milky Way, but it's not so much larger. So it's like 30,000 parsec. So a parsec is like 10 to the 13 kilometers. So it's 1 and 13 kilometers. So it's enormous. So how many stars is there in the galaxy is an important aspect as well. So there is like 100 to 400 billion stars in the galaxy. So if you want to have an idea of how big this number is, it's about the same number of dollars as in the Elon Musk bank account. So it's pretty big. Exactly. Elon Musk has 400 billion dollars. So in the galaxy, stars are being born, but they are not being born in a huge rate. So basically, we are forming about 1 solar mass of stars per year. So that does not mean that one star is born every year in the galaxy. It means that in total, all the stars that are being born are getting one solar mass. So it's important to remind you that the galaxy is mostly made of dark matter. It's like 95%. And the remaining of the mass is mostly made of stars. So 90% of the ordinary matter in the galaxy is made of stars. And if you look at the distance between stars, you will find that it's typically 5 light years, okay? 5, 10 to the 13 kilometer. So basically, the galaxy is mostly not made of stars in terms of space, okay? The stars are very far from each other. So what is between stars? So between stars is what we call the interstellar medium. So this is what is not stars in the galaxy. So the interstellar medium, or ISM, is basically 10% of the mass of the galaxy that is not dark matter. And it's mostly made of two components. There is one hot component, but very low density, which is called the hot or warm interstellar medium. It's like 95% of the volume of the galaxy. And the temperature are between 1,000 Kelvin and 1,000,000 Kelvin. So it's very hot, but it's also very, very low density. It's less than 1 particle per cubic centimeter. So if you cannot really understand this number, just consider that the air that we are currently sitting here is 10 to the 19 particles per centimeter cube. So the interstellar medium is much less dense than the air. But there is a slightly denser component in the interstellar medium that is called the cold neutral medium, which have also molecular clouds and dense core within it, which is 5% of the volume, but has a lower temperature. It's about 10 Kelvin. And the density is slightly higher, and in the densest regions, it's way higher than the diffuse interstellar medium. So you go from 10 particles per cubic centimeter to 1,000,000 particles per cubic centimeter in what we call dense core. But there is something interesting and funny about dense cores, which is that they are still much, much less dense than the air, because 1,000,000 compared to 10 to the 19 is almost nothing. So now we are going to move to only the cold interstellar medium, because this is where stars are being formed, and more particularly, they are born in what we call molecular clouds, which are also called stellar nurseries. So here I show you an example of the Perseus molecular clouds. So this image is about 100 parsecs, so 300 light year, and 100 parsec is about 10 million astronomical units, so 10 million times the distance between Earth and the Sun. And these molecular clouds are where the stars are going to be formed. So they are mostly made of dihydrogen, like the interstellar medium. There is a bit of helium, and there is also 1% of tiny dust particles that are very interesting because they allow us to see this image. With the gas, we will not be able to really see the molecular clouds. So these molecular clouds typically live like 1,000,000 years, and they are 1% of the volume of the galaxy, but they represent 50% of the mass of the interstellar medium. So now we are going to move to the densest regions of the molecular cloud where the stars are being born. So they are called star-forming clumps. They are so dense that when you look in visible light, you don't see through them. Here, this is an image taken by Hubble of the very famous pillars of creation. So this little arrow is about 1 light year. And we don't really see nothing because it's so dense, we don't see what's inside. But if we move to longer wavelengths and look with the James Webb Space Telescope in the infrared, we can see a bit deeper, and we see that within the cloud, there are some parts that appear still dark, like here. And these regions are the dense core where you are going to form eventually a star. So let's move to one very famous dense core that is called Barnard 68, which is one of the first ones that was observed. So you can see that it's so opaque that you don't see the stars behind the dense core. So this image is actually a bit funny because if you look on the internet, sometimes people are saying that this is a gap in the universe where there is nothing. Actually, it's exactly the opposite. It's dense, and so you don't see what's behind, okay? So dense cores are typically of the order of the solar mass, which is normal because they are going to make a star eventually. In terms of size, they are much bigger than a star. They are like 10,000 astronomical units. And they have density of 1,000,000 particles per cc. So we are still very, very far from building a very compact object that is going to be a star. So what is going to happen? So because the dense core is still relatively compact, it starts to feel its own gravity. And eventually, the gravity is going to be compensated by the other force, but it can eventually win. So what force can compensate the gravity? So like in a star, there is pressure. So this can act to support the cloud against its own weight. There is also turbulence. The cloud is agitated, and this agitation can also compensate the gravity. And finally, there is another force that is probably less expected, which is the magnetic force. And all these three forces act to compensate the gravity. But the thing is that the cloud itself is not totally isolated. It's connected to its environment, and it can get mass from its environment. And if its mass reaches a certain threshold, that is called the Jeans mass, the gravity is going to win. And if the gravity wins, the cloud is going to collapse under its own gravitational force. This is called the gravitational collapse, and it is what is going to give the birth of a star. So we don't have really good images of the gravitational collapse, because when you see the universe, it's a bit static. We have some protostars that we think are collapsing, but what I'm going to show you is a numerical simulation, which is another way to look at this kind of objects. And this is a simulation that I've made with the RAM6 code. So for now, it's dark, but as the density is going to increase, the colors are going to get brighter and brighter, and you are going to start to see the star. If I launch the video. Wow, it's beautiful.
Amazing.
Yes. Okay, it's increasing.
Wow.
Voila. Okay, so there is a bright object at the center, which is the protostars. To be exactly honest, we don't really resolve the star, but there is something interesting that happens, and that was not something I told before, which is around the protostar, you see some flat structure that is called a protoplanetary disk. So why is that? Because the core is in rotation. As the core contracts, the conservation of a quantity that is called angular momentum is going to accelerate this rotation. And eventually, the rotation can compensate the gravity at the very center of the collapse. And then you will need a flattened structure to form, to be in equilibrium. And this structure is called the protoplanetary disk, and it's where the planets are going to be formed. So here is a very nice observation done by the James Webb Space Telescope of a protostar that is being formed. And if you look at the center, there is some thin dark layer that is the protoplanetary disk seen from the side. And since it's from the side, the light does not pierce through, and you see a very tiny bar. You can see it here circled. You can see it even better in this other observation done with a very large telescope. It's the same thing, but the disk this time is a bit tilted. And it's funny, it looks a bit like a hamburger. So on the top, the surface of the disk is illuminated by the star. But on the side, the light does not penetrate, which is why you have a dark layer. But you can clearly see that the disk is some kind of flat, roundish structure. So there is an even better way to see deeper in the disk, which is to go to even longer wavelengths, because this image before we are seeing in the infrared. You can go even beyond and see in the millimeter. And if you look at the millimeter, you are going to probe the very inner part of the disk, and you are going to start to see very nice structures that are indicative of something going on within the disk. And this thing is planet formation. So just little numbers. So these disks are typically between 1,000 and a tenth of a solar mass. So it's lower in mass than its own star. And they are very flat structure. So the scale height of the disk is about 5% of the size of the disk. And they live about 10 million years. Okay, we know that there are planets that are going to be formed in disk. And why do we know that? Because since 95, we have now explored the planetary system of 5,000 systems. And if we extrapolate these numbers and take into account our bias of detections, we can predict that at least every star in the galaxy is going to host one planet. So that means that planet formation is a very common process that must happen in every disk. but we don't really know how it happens because we are starting from very tiny particles that are called interstellar dust grains that are less than 0.1 micron. So it's much, much smaller than a planet. So how this tiny speck of dust is going to form a planet is a very, very important question. So here you notice that I don't really have any nice observations because as we probe deeper and deeper, our resolution starts to be worse and we don't really see so well. So we have only ideas on how planets are really formed. So we think that at the beginning, the dust grains are going to collide together and they are small and they are going to stick. But eventually, as they get larger and larger, the energy of the collision is going to be so high that the collision are going to start to be destructive. And so there is going to be a size above which we cannot stick the grain anymore. And at that stage, we are about at millimeter in size, so we still are very far from a planet. We need other process to grow even more in size. So we think that in the disk, some tiny instabilities are going to concentrate the dust to allow another gravitational collapse, but this time on the dust. And this gravitational collapse is going to lead to formation of bodies that are a bit similar to the asteroids we have in the solar system. And then these asteroids, they are starting to be big, and so they can stick again when they collide because of the gravitational force. And like that, we are going to build some objects that have the size of planetary cores, and these objects are going to sweep through the dust that is in the disk to grow even more in size. Here we are reaching about the size of the Earth. And what is interesting is that for some objects that can grow because they have a lot of material around, they can start to grow so much then their gravity is going to attract the gas on their surface. And this is how you are going to form, for example, a giant planet like Jupiter. So here you notice that I've put certain objects of the solar system, and basically the size of these objects can tell where the process stopped for this object. So for the Chury comet, the growth stopped at the planetesimal collision. For the Earth was able to collect some dust and grow in size. And Jupiter was so big that it also accreted the gas in its vicinity. Okay, so that's basically sun, all the stars and the planets are formed. So if you want just to know a bit what I'm doing in my research, so I'm a numericist, which means that I run numerical simulations. I don't really do observation. What I do is that I use codes to solve the equation of the evolution of fluid. And this allows me to model how stars are being born. And then I can compare this simulation to observation to try to understand what is happening. And I'm particularly focused in how these dust grains are going to collide together to grow to size of the order of the millimeter. So thank you for your attention, and I'm happy to take any questions now.
Amazing talk. Okay, I'm very excited because yes. Okay. Yes, now it's time for questions. And in order to motivate people to ask questions, I'm going to give either a bookmark or a sticker that you can choose. If you have a question, so please, no, you don't have a question, so no. Okay, let's go to the first.
And if I answer question, do I get a bookmark? Yes. Oh well. No.
Thank you. That was very nice. I got a bookmark. Okay, so my question is, when things are colliding
You mean about the dust?
When things are colliding, when the grains are colliding, is there? I'm interested in what the molecular composition is. Is there any molecular interaction happening at that point, or is that just the force of gravity slamming things together?
For the grains, it's like a van der Waals force that sticks the grains together. For the planetesimals, it's more gravity, which is why actually we can stick them again together. Yeah. So it's this kind of electrostatic forces.
So at the van der Waals level, do you have to do like any kind of? Did you model those reactions?
So there are some lab experiments actually, interesting astrophysics in a lab that are trying to measure the surface energy of dust particles and to make them collide, also to see what is the outcome. So this is how we know actually that you can also do some analytical calculation and derive some properties, but some of the properties are actually measured in lab experiments. So they are trying to reproduce the condition of real protoplanetary disk, but the thing is that a disk, so you see it's a dense object, is still more empty than any vacuum that we can produce in a lab. So we have to trust a bit this experiment, but there are still some lab experiments that are done. Yeah.
Okay. Thank you. Yes, I saw a question over there.
Is there a relation between the planetary disk and the accretion disk in a black hole?
Well, they are not the same accretion disks, but they are both, in a sense, accretion disks. Although it's true that for the protoplanetary disk, there is a little doubt right now that is actually really an accretion disk, because there is also winds that are triggered by the magnetic field. That means that maybe some of it's not a viscous disk like in black hole. The accretion will be powered by the winds. It's a bit different. But they are not the same disks. They are not the same objects, but they have similarities.
Cool. Any other questions? Somebody wants a sticker.
What is maybe you said it, but I missed it. So what is the time scale to form these different type of objects? And does it vary from
which object, for example? For the star, I mean, the stars, it will depend.
No, sorry, for stars. Like,
so for star, actually, Matthew probably will give better accurate answer. But for the stars, it will depend on the mass. Okay. So I know for the sun that we expect its main activity of nuclear fusion to last like 10 billion years.
No,
for forming.
forming.
Okay. For the gravitational collapse. Yeah. So it's about tens of thousands of years. 10,000 years. A bit more. It depends on the size of the cloud.
And it depends on the size or on the composition?
It actually depends on the density. So there is a characteristic time scale that is called the free fall time scale that only depends on the density of the cloud. So a cloud of 10 to the 6 particle per cubic centimeter is going to collapse slower than a cloud of 10 to the 7, for example.
But, yeah,
so it's like between a couple of tens of thousands of years and like 0.1 million year, something like that. No problem.
Great. Any other questions? Oh, in the back. Amazing.
Thank you. Can we see behind those clusters in other emission range than the visible emission range? Or that's so dense that no emission goes through? Yeah.
This one? Okay, sorry. Well, actually, you have your answer here, but
yeah.
So,
core.
This is in the visible, actually. So there are images of this cluster in the infrared, and you see through. This one is not so dense because actually it's before the collapse, so it's less dense than.
Before the collapse, can we see behind the core?
Yeah, you can see behind this one in the infrared, actually, or in the millimeter. You see, actually, you can. If you look a bit, the screen is not so good, but you see on the border of the cloud that the stars are a bit redder. So if you go even to redder wavelength, infrared, you will start to see even in the center.
And can you see gravitational effects on those emissions?
No, it's a very low mass object. Okay. It's not.
Not dense enough.
Not massive enough.
You have to choose a sticker, or let's take one. Okay. Any other questions? Who wants a sticker? Don't be shy. This right. Oh. Okay.
Yeah, of course. Actually, on the if you go back to the pillars.
This one or the other?
So, what is the impact of the 3D structures of the clouds on the formation of stars? Because here, what I thought that it's in like the tiny.
They are like pillars, basically.
Yeah, but like, do you form stars also in the middle where there is nothing?
Well, there is
like shape.
Actually, if I go to the other wavelengths, you can see that there are shapes even inside. So actually, any kind of shape could collapse in principle. If it reaches its critical mass, it can collapse. Okay. So actually, why are there pillars is also an interesting question. So this exactly. So because there is actually some stars that are massive, that are emitting a lot of radiation that is pushing the gas together. So before the star has formed, there were no pillar, and there was still collapse happening within the cloud. So the pillars are shaped by external, let's say, radiation of stars, but that doesn't prevent collapse. So this arrow that we don't see in full is about 1 light year. So like a pillar is 2 light year basically, between 2 and 3 light year. So it's pretty huge actually. Yeah.
He wants another sticker. Actually, I want my own sticker, but this is not related to your talk. Can you explain your shirt, please?
Well, so the dinosaurs is actually, so the dinosaurs they received from the solar system a nice planetesimal, and because they didn't know what it was, they were not able to like prevent anything, and they basically died off. So they didn't have a space agency to deflect, let's say, the planetesimal. That's a bit sad.
Yeah.
Yes.
It's from ESA, I see.
Yes.
It's from ESA.
I never worked at ESA actually. But I still have a sticker, but yeah.
Any other question around here? No. Okay, if there are no more questions, let's thank again the speaker.
Thank you very much.
Woo!